Okay, so we are recording 8.2 and trying to get sound with it this time, so I'm using my phone. So hopefully that will work. So we are looking at probability, and we're going to look at the dice example. So if you have your chart with the 2 dice thrown, we're going to look at that. So Wednesday we made a chart where you threw a 2 dice and you had a column 1 through 6 and rows 1 through 6, and you showed the total possibilities there. So if you have that chart, then you can pull it out and we'll take a look at it. And we'll do some probability with it to see if you are understanding the different kinds of probability we looked at. So we had the black dice 1 through 6 and the red dice 1 through 6, and when you throw those 2 dice, we listed all the possibilities. So there were 36 possibilities. So remember how you calculate probability? We have the total possible outcomes. So when we're looking at the dice, the total possible outcomes with 2 dice would be 36. And then we're going to look at the probability of a particular event out of those 36. So first we're going to look at what is the probability of rolling 5 or less. And that's going to be with 2 dice. So what is the probability of rolling a 5 or less with 2 dice? So we just go ahead and look at all the different outcomes that made a total of 5 or less. Here's the definition of probability. We take the number of different outcomes in the event E, so that would be, for our case, rolling 5 or less, and the total number of equally likely outcomes. And then in our case, that would be 36 equally likely outcomes. So we'll go ahead and take a look and see how many of those outcomes that we listed resulted in 5 or less. So out of the 36 possible outcomes that we put in the bottom of the fraction, we pick out either 1, 1, or 2, 1, or we could have 1, 2. There's some more options: 3, 1, 2, 2, 1, 3, 4, 1, 3, 2, 2, 3, or 1, 4. All those options, in fact, that are above this line. Looks like 10 if you count up all the different options that there are. So the black one with the red 4 is different than the black 4 with the red 1, so you have to count those separately. So we have 10 different options out of the 36 equally likely outcomes when you throw 2 dice. When you put that in your calculator, 10 divided by 36, you get 0.28. So that's the probability of rolling 5 or less. Now we're going to check out with 2 dice. What is the probability of rolling a total greater than 5? So what would be the probability of rolling a total greater than 5? So you can look at your chart again. You still have 36 equally likely outcomes for the bottom of your fraction, but now how many outcomes will be greater than 5. So you can go ahead and check that out. So one of the students pointed out that you could just subtract, because if you're not going to have 5 or less, then you can subtract the probability of 5 or less from 1. So we have 1 minus 28, 1 minus 0.28 or 0.72 for a probability of more than 5, or 26 over 36. So when we look at probability of rolling the 2 dice, you either get 5 or less, or you get more than 5. So the total between those two probabilities is 1. You're either going to get 5 or less, or more than 5. So we're going to write out that statement from our textbook. If the probability of P of an event happening, then the probability of P not happening is 1 minus P. So if probability is P of an event happening, then the probability of P not happening is 1 minus P. So we'll just look at a few of our definitions in our book that we've been looking at. This is the event either happens or it doesn't, so it just reemphasizes what we just wrote down. If a probability is P of an event happening, then the probability of P not happening is 1 minus P. Well, I'd like for you to try a few probabilities on your own. So let's write a few down for you to try and see if you're getting the hang of. So again, with 2 dice, find the probability of rolling doubles. So doubles would be like 1 on each dice or 2 on both dice, so on. Okay, and then another one to try. Find the probability of not rolling doubles. And here's another one. Find the probability of an even total. Okay, so find the probability of an even total, like 2 or 8 or some other even value. So you can use the chart there. You can go ahead and find which out of the 36 possible equally likely outcomes fit A, B, or C, and see how you do with that, and then we'll compare. As you're working on these, students, if you have any questions, you feel free to email me, okay? If you're looking at some probabilities and wondering if you're figuring them out correctly, feel free to email me. And your homework on your 8.2 your 8.2 Mindscapes is designed to help you verify that you know how to do probability as well. So what did you figure out for the probability of rolling doubles? Did you count up the ones where you had doubles? The 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6? Okay, you should have got 6 out of 36 possibilities. Now you can put that in your calculator. If you put that in your calculator, you get 0.17. And that means you could calculate the probability of not rolling doubles as the other 30 options. So 30 out of 36. Or you could say 1 minus 0.17. Either way, you should get the same thing. So 30 out of 36 or 1 minus 0.17. They should both be equal the probability of not rolling doubles. So you're just counting how many of those options in the table are not doubles. And then what did you get for the probability of an even total? You should have gotten 18 out of 36. So 18 of the options out of these 36 were even. So that's 0.5. So we just want to make sure you know how to do these pretty straightforward probabilities. Count up the total possible outcomes, and out of those outcomes that you would write in the denominator, write in the top of the fraction how many of the outcomes are the outcomes that are described by your event. Now we're going to look at playing Yahtzee. So how many of you play Yahtzee? Okay, we're going to talk about finding pairs of dice when you're rolling more than 2 dice. So first we'll look at the probability of a pair when rolling we're going to work up to finding the probability of a pair when rolling 5 dice. Remember, what we were doing in this section is looking at simple things deeply. So we don't start with 5 dice. We work our way up. First we'll start with 3 dice. And in fact, before that, we might as well write down the probability of a pair with just the 2 dice. We already found that out though, right? So the probability of a pair with 2 dice, that was 6 out of 36. I'm just checking what that was. I think it was 0.17. I got it. Yep. And then we'll add a dice. Okay, so now we'll say there's going to be 3 dice. So the probability of a pair with 3 dice. Okay, so just 2 of the 3 dice have to match. And what is the probability of a pair? So now we have more than 36 options. So we have to count all the possible options when rolling 3 dice. Now we're going to take the approach of rolling, calculating when you don't get a pair. So it's easier to calculate not getting a pair when you have 3 dice. Our probability of 0.17 was 1 minus 0.83, the probability of not having a pair with 2 dice. And we're going to take that same approach with 3 dice. Instead of counting how many give us a pair, we're going to count how many options are not pairs. And then say 1 minus the probability that we don't get a pair. So the probability that we don't roll a pair with 3 dice. So we'll have 1 minus, and now we have to count how many possible options there are altogether with rolling 3 dice. So think about your table that went 6 across and 6 down with 2 dice. Well, every one of those options now could have another 6 options. So we're going to have to look at the possible outcomes, and in the top of that fraction we're going to put the possible outcomes that are not pairs. So let's think about how we can look at the possible outcomes that there are altogether. Your author has a nice picture for this. So on the in the textbook you have the front of this cube, which would be all 36 representations like we drew out. So you could get a 1 and a 1 in the upper left corner, or in the bottom right, a 6 and a 6. But now each one of those 36 options, each one of those, like this 1 and 1 that we'd have in the front, that could have 6 other choices with it. So every single pair that we had could have 6 more choices now when you add that third dice in. So like you could have the 1 and the 2, the yellow 1 and the green 2. Well, that could go with a red 1, or a red 2, or a red 3, 4, 5, or 6. So every single one of the 36 options that we saw at the beginning with just 2 dice now has 6 more dice that could be 6 more options on the dice, the third dice that we're rolling with it. So when we're listing all the possible outcomes, we get this huge cube. There's the original 6 times 6 outcomes, but then each one of those 36 possible outcomes could have a different number with it. So we're going to take the original 6 times 6 and put another times 6. So all the possible outcomes with rolling 3 dice would be 6 possible choices for the first dice, 6 for the second dice, and 6 for the third dice. So that's all the possible outcomes. Now we have to think of which of those are not pairs. So which of those possible outcomes do not have pairs? So you have to be careful with your counting and not double count. So let's look back at when we had 2 dice. Okay, so when we had 2 dice, you could have a 1 and a 1, that was a pair. Or so we didn't want that one. So once you have a red 1, well then you could have a green 2, or a green 3, 4, 5, or 6, but we could not have a red 1. So the red 1 could have 5 different greens with it, just so it wasn't the 1. Similarly, for each one of the red dice. So every time you pick one of the 6 options for the red dice, well, the green dice has to be one of the 5 other options possible. So if your red dice is a 1, then your green dice can't be a 1. It has to be 2, 3, 4, 5, or 6. So each red dice has 5 different options to go with the green dice, and that's how we got that 30 options that were not pairs. But now we have another dice in the mix, so that third dice mustn't be what the red dice was, and it mustn't be what the green dice was, so it has to be one of 4 other options. So once the red dice is thrown, there's only 5 options to not be a pair for the green dice, and then the last dice only has 4 options, so it's not the same number as either the red dice's number or the green dice's number. So these are all the possible outcomes that are not going to be containing a pair. So if you have a yellow 1, then you can't have a red 1. You have to have one of the other 5 numbers. And you can't have a green 1. And in fact, the green dice can't be what the red dice was either. So the green dice only has 4 options. So what we've calculated in this fraction is the probability of not having a pair. So we have 1 minus this number, that's the probability of not having a pair. Now if you have a scientific calculator where you can put parentheses in, you can put this all in your calculator at once. And I'll show you that there. So you put parentheses around the top part of the fraction, the numerator, and parentheses around the bottom part of the fraction, the denominator. Otherwise, if you don't have a scientific calculator, you can calculate 6 times 5 times 4, and then 6 times 6 times 6 separately, and then do the division afterwards. So we find the probability of not getting a pair is 0.56. So the probability of getting a pair is 0.44, 1 minus 0.56. So the probability of rolling a pair when you throw 3 dice is 0.44. So this is a pattern that we can work and continue with. We can look at the probability now of rolling a pair with 4 dice. Okay, we just use the same pattern. We take 1 minus the probability of not having a pair. Okay, and you see that we had the pattern, the 6 times 5 over 6 times 6 for not having a pair, and then we just put in 1 more dice, so that made the numerator and denominator have more options. So we had, by the way, you should never decline on your mom. I'm only doing that because I'm talking to you and I will call her back. Okay, so we're adding in 1 more dice. 6 times 6 times 6 in the denominator for that next dice, and then 6 times 4, 6 times 5 times 4 in the numerator, and that pattern continues now when we put in 4 dice. So the probability of a pair with 4 dice, can you go ahead and write that out, what you would expect that probability to be? So you would be calculating 1 minus not getting a pair with 4 dice. So you want to list all the possible outcomes, and then there's 4 dice now. So if you wrote 6 times 6 times 6 times 6, that was correct. And then what did you put in the numerator for not getting a pair? Hopefully you put 6 times 5 times 4 times 3. Because now whatever this first dice is, the first dice can be any of 6 numbers, but once the first dice is thrown, the second dice can't be that number, so it only has 5 choices. And then the third dice can't be either of the numbers of the first 2 dice, so there's only 4 choices. And then that last 4th dice can't be what any of the first 3 were, so there's only 3 choices for that. So we go ahead and calculate this out. 1 minus the probability of not getting a pair with 4 dice would be the probability of getting a pair with 4 dice. So 1 minus 0.28 or 0.72. Well, let's see finally the probability of a pair with 5 dice. So people who play Yahtzee can know how likely they are to get a pair with 5 dice. Now this doesn't tell a particular pair, just any pair at all. And we'll just continue this pattern. So we would say it's 1 minus not getting a pair with 5 dice. And we can go ahead and just follow the pattern. So now in the denominator, when we look at all the possible outcomes, all the combinations of different dice that we could get for 5 dice, we would have 6 times 6 times 6 times 6 times 6 in the denominator. So 5 6's multiplying together in the bottom of the fraction. And then the top of the fraction, we continue the pattern as well. So 6 times 5 times 4 times 3 times 2. So we're looking at the probability of not getting a pair with 5 dice. So whatever the first dice is, the rest of the dice can't be that number. Whatever the second dice is, the rest of the dice can't be that number or the first one. And so the numbers just get smaller as we have less options available to avoid a pair. So we'll put that in the calculator and get 1 minus 0.09 or 0.91. So 0.91 or 91% chance of getting a pair when you roll 5 dice. So sometimes it's easier to calculate how likely you are for an event not to happen, and then we use 1 minus the event not happening to see the probability of the event happening. And that's the case with these. It's easier to count because that's what we're doing, right? We're just keeping careful count. We don't want to double count anything. We don't want to miss counting anything. Now, do you remember when we talked about the probability of having a shared birthday? We said that the probability of having a shared birthday was 90% with 41 people in the room, which seemed really, really different. So we're going to look at the probability of matching birth dates and see why the probability came out like it did. So what do you think the probability is with 2 people? When you just run into 2 people, what do you think the probability is that you would have a shared birthday? We'll just ignore leap year, by the way. So write down what you think the probability of you having the same birthday as another person that you run into would be. I'll give you some time to think about it. So now we're just looking at 2 people. With 2 people, how likely is it that you have the same birthday as they do? Okay, well, there's 365 possible birth dates, so we put that in the bottom. And we're counting how many would have the same birthday as you. Well, there's just one of those days, right? So 1 out of 365. We're going to take that approach from a different direction, so we can add on people. Like we added on dice, we're going to add on people. So we're going to look at this from the other direction. We're going to look at the probability of matching birthdays by finding 1 minus the probability that the birthdays don't match. And you could read about this in your textbook as well. So that might be a little easier for you to understand if you want. So we're going to say 1 minus the probability that birthdays are not the same. So just like with the dice. So 1 minus the probability the birthdays don't match. So we have to think of all the different ways the birthdays can be combined for the bottom of the fraction and all the ways that they don't match for the top of the fraction. So all the different ways the birthdays can be combined, that'd be 365 times 365. And we're just picturing there that table of dice that we made. That was just 6 across and 6 down because there was only 6 options on the dice. But now we're thinking of a table 365 across and 365 down for all the different possible combinations of two persons' birthdays. So in the numerator, we're trying to find out how many are not pairs. So the ones that aren't pairs, the first persons can have 365 any day. Okay, so again, reviewing with the table, the first dice with one dot on it you can think of as January 1. The dice with two dots you can think of January 2nd, and think of this going all the way across, 365 days across and 365 days down. So first, in where we have 1-1, you could think of that as January 1 and January 1. So that's a pair, and we don't want that pair. So if we're avoiding a pair, then if we have a red January 1, then we have not a green January 1, but we could have green every other day. So there would be 364 days across that were not January 1. Okay, so once a birthday is picked, we don't want that green person to have that birthday at all. And we do that for every single option for the red dice, or the red birthday person. So every 365 choices for the red person, or red dice, we have 364 that we cannot, that we would choose from, so that we don't match the one birthday that's the three that came out with the first person's birthday. So first person can have any birthday they want out of 365 days, but then the second person has to avoid that day. So there's 364 choices to go with every single day of the year that was possible for the first person. So we'll go ahead and calculate this and see if it comes out to be the same. So 1 minus the probability that the birthdays don't match equals the 0.0027 probability that the birthdays do match. So 1 minus 0.9973 is the 0.0027. So we have in the denominator all the different possible combinations of two persons' birthdays, and in the numerator we have all the combinations that do not result in a match. So they're not going to match in 365 times 364 different ways. And then we can go on and follow this pattern through with three people. So you'd have the 1 minus the probability that the birthdays, 1 minus probabilities that the birthdays don't match. You have 1 minus 365 times 365 times 365 total possibilities in the denominator, just like our cube with the 6 dice. Okay, so we had, we had 3 dice, but we had 6 options for each. So now think of this cube stretching back 365 squares instead of just 6 squares, and being 365 squares tall and 365 squares wide. So all the different combinations that we could get with 3 different people's birthdays. Now the first person can have their birthday any day of the year, but then the second person, we're looking at birthdays not matching, so the second person has 364 choices, and then the third person can't be either of those two persons' birthdays for us to not match, so that would be 363 choices. So we're looking at all the different ways you can put together birthdays that do not match. We'll put that in the calculator. So we'd have 1 minus 0.9918 or 0.0082. So still very low probability that when you have 3 people, the birthdays match. Because remember, the probability that we end up calculating there on the right, the 0.008, that's that the birthdays do not match. I'm sorry, that is the probability that the birthdays do match, that two people share a birthday when there's 3 people together. And with 4 people together, you can follow the same pattern. We're going to find with 4 people the probability of a shared birthday among them. So 2 of the people having a shared birthday. And it will be the same pattern. So you go ahead and write that down. So you're calculating 1 minus the probability that the birthdays don't match. No shared birthday between the 4 people. So that's the same pattern, 1 minus 365 times 364 times 363 times 362 over 365 times 365 times 365 times 365. So in your calculator, that's 0.016. So we're getting larger numbers now, or at least up to 1% now, 1.6% chance. So you could go on with this pattern, but your textbook did it for us. And here you see on the page in the textbook where they calculated the probability continuing on like that with different numbers of people in the room. So when we get down to 40 people in the room, it's 0.89%, and that's why when you get to 41 people, it's 0.9%. Look at that, if you have 90 people, you're almost sure to have 2 people sharing a birthday, which is really counterintuitive. Remember when we talked about this, we thought, well, to have a shared birthday, a 90% chance of a shared birthday in the room, you'd need maybe like 330 people. So we have 90% of 365 days, something like that. And it turns out that's not what you need, not nearly as many. So probability is not always straightforward. This is a little trickier probability. It's not always intuitive. I have another example for you here with some cards that I brought. So let's take a look at those. So I have 3 sets of cards. They either have an X or an O on it. And then on the other side, there's one with an O and an O. So that's the O and the O. This one has an O and an X. And then the last one has an X and an X. So I have a question of probability for you. If we take those cards and I shuffle them all together, okay, and then put one down, so I'm shuffling them and putting one down, and it's an X. What is the probability that this X has an X on the other side as well? So remember, there was an O and an O, an X and an O, and an X and X. And my question for you is, what is the probability that this X has an X on the back of it as well? So think about that and write it down, and we'll talk about it. So some students were telling me what they thought. So some of their ideas they had. Okay. So the cards again were OO, XO, and XX. And some of the ideas the students had, they suggested a probability of, I guess I'm going to go right to it. So you get an OO with that, or an XO with that one, or X or an O, or an XX. So when we're just looking at one side, this is what we'd see. With the OO card, you'd see an O or an O. With the XO card, you'd see an X or an O. And with the XX card, you'd see an X or an X. Okay, so those two probabilities are gone. We did not see OO, and we didn't see that one. So these are the three options that we saw. So as we're figuring out probability, these are the three possibles that we saw. So this would be the denominator of the fraction. So there were three possible, and of the three, two actually resulted in an X on the other side. So only the bottom two X's would have an X on the other side. And this particular card did turn out to have the X on the other side. So there was a 2/3 probability that there was an X on the other side because there were three possible possibilities in our event, in our outcomes that we had, the ones that showed the X, and of those, two would show an X on the other side when you flipped it. So that was a tricky one. We talked in class about why you could have chosen 1/2 or 1/3 and made a good argument for that, but it turns out with this one it's 2/3. So the probabilities that I'll ask you on a quiz will be more the type that we did at the beginning with the table of dice. There was 8.2 Mindscapes you can do now, so those will be due for you online students Sunday night. And I had to cancel class for Monday before it snowed, but class is canceled anyway, so that worked out good. Okay, see ya, bye.